So we have the pleasure today to welcome Harold Erbin, who is now working at IPHT, so Institut de Physique Théorique, au CEA, so it's at Orme des Merisiers. The building is at the back of Orme des Merisiers. But Harold today is going to talk to us more about works that he has done when he was a Marie Curie Fellow in between MIT and CI, if I'm not mistaken. So, on a dialogue between machine learning, geometry, and quantitative theory.
Thanks a lot for the introduction and also for the invitation. Then I will try to review several works I did at the interface between machine learning, math, and physics. So the goal here is to give a taste of the problem we want to solve and why we want to address this problem. So I will try to limit the math as much as possible. But because there are so many topics, if at some point you want me to clarify a bit something, don't hesitate to tell me. So first, I would like to thank my collaborators. So Atakan, who is a PhD student at MIT, and we go for a postdoc at UC Davis. His PhD advisor and my Marie Curie advisor, Barton Sieber at MIT. And then colleagues at CEA, so Ricardo, Vincent, and Dean, who are at the DRT and DES. So I will start first by explaining the general motivation of why there is this set of problems and why it looks so different, but at the end there is still some unity in the different topics. And then I will describe three different applications of machine learning and physics and math. So the first question we can ask is, where does machine learning fit in theoretical and mathematical physics? So we have many fields. So for example, cosmology, where you can have both for the simulations, but also for more like data analysis. You find it in lattice simulations, so it can help to boost or replace Monte Carlo simulations. But the place I'm really interested today will be in geometry and topology and in string theory. So why do we want to use machine learning in physics? So what are the typical problems we have? So the first is the big data. So we have some fields where you get just a huge amount of data and just you cannot compute everything for them. So it's typically things which are related to very big experiments. I will not talk about this first part today. I mean, a bit, but not for the experiments. The second problem will be the exploration problem. So if you think in particle physics, we know that the standard model is not complete. We have various problems. And so you have many extensions of the standard model of particle physics. The problem is that this extension are, so you have many of them, and often you add many parameters. So you can think about supersymmetry, for example. So you get this ton of models, and just you're not sure exactly which one will be good, which ones fit with the experiment, which one are the most promising, and so on. So you just have too many information, and you need a way to just navigate this information. The last one is computational, which will be the main, the core of the talk today. So it's when you have the interactions in your model, or the mathematical problem prevents you to do analytic computations. So you just can't solve the equations, and you need to find another way to extract data. So here, often we have some numerical methods, but what I want to show here is that machine learning can help solve a hardcore math problem, which we can reuse for application in physics after. So what are the main problems in theoretical physics? So for the standard model. So first, we can ask if we have a unique theoretical framework which can describe all the phenomena. The second problem is that in the standard model, we have many independent parameters, so around 20. So the question is, where does this parameter come from? Why do they take this value, and so on? So we would like some more unified description of them and just understand them from first principle. We have various unexplained phenomena like dark matter, dark energy, neutrinos, and others. And then you have also some theoretical problems. So this one, it's not like something which, if it remains, it's bad, but it doesn't sound very like aesthetic. So we would like also to get a better understanding of this problem. So to address these different issues, you have two ways of development. So first, you have quantum gravity, which means that you want to quantize general relativity. Because until now, we have really two theories. You have general relativity for large-scale gravitational system, and then you have the standard model of particle physics for all the subatomic particle and interactions. And it's hard to merge the two together. So quantum gravity, the idea is that everything should be quantum. So let's do it for general relativity. And then you have unification. So it's to try to find a common origin for the parameters, so that you just, so it's really the reductionism. So you just want to have one theory to explain as many things as you can. So before going to explain about string theory, which is one attempt to solve the problem of the previous slides, I just want to have a very brief one-slide introduction to quantum field theory. So QFT, it's a language of modern theoretical physics. So basically everything we do, in general, at some point, we will use QFT to solve it. Some people will speak about Euclidean or statistical field theory, but I will use this as a synonym. And the main idea is that to each physical object, you will associate a field, which is just a continuous function over space-time. So now, when we have this field, we don't want to see each object of a specific kind as unique, but we just want to see them as excitation of this field. So you can imagine your field just being there over space-time. And when it gets excited like a wave on the sea, you interpret this as an object. But if the field is just flat, then you don't have any excitation. So now you can see space-time to have many such fields. So you can have the electronic field, a field of photons, so it's the electromagnetic field and so on. And this field will make many layers on top of each other and interact. So for example, if you have a positron and an electron, they can interact together to make a photon, like here. The upshot is that it's a very convenient language. We also develop many tools to understand this. We also believe it's a fundamental description of nature for many aspects. So we want to reuse this language as much as we can. So now the question is the following. So if you look at particle physics, in the name you have particles. So particles are just like point objects. So when a point is fundamental, it means you cannot find any structure. So if you look at the photon or the electron, you cannot say the photon or electron is made of something. It's just what it is. Now you can ask the question, what happens if I try to describe fundamental extended objects, so like a strings or membrane? So here you imagine some object which extend in this way, for example, or like this. But by fundamental, you say, okay, there is no substructure. You cannot do that on the right-hand side. So for example, take your string and zoom and see that in fact your string is made of many atoms. Or you don't want to see the string as some like other membrane wrapped around itself and made very tiny. An analogy would be, for example, the protons or neutrons. We know that they are made of quarks. So protons and neutrons are not fundamental. So you want to have the subjects. And now you can ask, what happens if I want to write a theory and either a quantum field theory of the subject? So the simplest case is string theory, because you have the particle, you just extend the object in one dimension, it's a string. So it's the simplest thing you can do, so you can start to study that theory. And here we find many great results. So first you get a theory of quantum gravity. You get a unification of matter interactions and gravity. You don't have any divergences. So here to explain briefly, so in the standard model of particle, you find many divergences, but you have a way to cancel all of them. But if you want to add gravity and just quantize it naively, you find many infinities you cannot cancel. So the question is, like, what can you do? And it proved very difficult to tame this divergence, but string theory, you can just prove that they are not here, they just, everything is finite. You get also a fixed number of dimensions, so it's very rare to have theories which predict the number of dimensions. Okay, it's 10, it's bad. I will come back on this just after. You have no dimensionless parameters, so you just have one big theory, and from this you can in principle deduce everything. And it also implies the existence of branes of every dimension. So it's good because you're like, okay, I started with strings, but I should incorporate all possible fundamental objects. So now once you have this, then you can ask, okay, here's my package. Does it describe reality or not? This is another question, but at least it's a consistent package, so you should study it. try to understand it better, understand the prediction, and if it doesn't describe the realities, then you should explain why when you see that in principle it's possible. 2 points about string theory. So first, we didn't reproduce the standard model of particle physics, and we have no falsifiable or feasible experimental prediction. So for now, it's just a theory, and we have no idea if it's really the real theory. If you have a string theorist, you will say, yeah, we are the best, so it's true, but I don't think it's a good argument. So we should just work harder. Okay, so now we go a bit more in the details of how we do string theory. So the main goal is really to find, I mean, for me at least, to find the standard model from string theory to really show that, okay, it's compatible with what we have observed. We can describe all the physics we know with string theory. So the way is that you start with superstring theory in 10 dimensions. As I said, 10 is bad because obviously we live in 4 dimensions, so 1 time and 3 space. So you need to reduce from 10 to 6. So then you do what we call the vacuum choice or flux compactification. Here just to say, okay, I want to see my string evolve on some space-time. Just because you need to first like fix some space-time even if it can fluctuate. And it happens that for mathematical reason, you need what is called the Caraballo manifold. So I will not explain why, but I will explain some computation with Caraballo later. You need also flux, so generalization of electromagnetic flux, which you have. When you do this, you go to 4 dimensions, and then you just want to keep what you can see at low energy. So you should imagine that it's a theory of quantum gravity, so most of the particles, I mean, most of the things you could see are way too energetic to appear at our scale. So we just want to go back to what we can see and observe, and obtain a effective description of this and see if we can match with a standard model. Okay, we should also check the consistency and then read the 4D model. So it's all the steps you must do, but at each step, except the first, you have a lot of mathematical challenge. So one challenge already for this full procedure is that you have no selection mechanism for the step 2, which means that you don't know really which vacuum choice you should make. Like there are many possibilities I will show after, way too many. And it's what people call the string landscape, which means that you just have a very big set of possibilities and you don't know what you should do. So now you are ready to this idea of mapping the landscape. So the first goal is to already find consistent string models. Then you need to find generic and common features, because then you can say like, okay, I cannot reproduce the standard model, but I know what are common things which I can try to look experimentally. Or at least if your string theory is always telling you, here is what I get, and it's just opposite to experiment, you can start to get a bit worried. And okay, they reproduce a standard model. So you have different steps. So understand how you do you study the Caraballo manifold, find parameter distributions, and so on. And one way to also address this computation is to construct a quantum field theory of strings, on which I will come back later. So you have a bit this picture. So here you have like string theory at some very high energy scale, which you cannot observe. So we can just observe the low energy, which is the plane here. And you see that string theory is like projecting on this plane. And because you have many ways to project, it's kind of a big space. But you have many more theories. So the question is how you can try to move inside this red area of what is string theory, and also find the point here, which is a standard model. So to give you a taste of why it's difficult, so let me count the number of geometries which appear in this problem. So if you look at Caraballo manifold, the simplest type is called complete intersection. So for the 3-dimensional one, you have around 8,000, which is big but still manageable. For the fourfold, you have 1 million. Then you have another family which is a bit bigger, so which you build from polytopes. Here you see that it's 500 millions polytopes. From each polytope, you can extract a few Caraballo, and there is some bond here 10 to the 400. So as you see, it's big. Now you can add fluxes and other information, and you get this kind of number here. So as you see, you cannot do them one by one. It will take too much. So we need another way. So machine learning is kind of already here an indication that we need to handle very big data in string theory. But there is more. So before going to that other more mathematical problem, let me speak about string field theory. So the idea is to write a quantum field theory for string theory. So it's a field theory of extended objects. It's interesting, as I said, because QFT is the modern language of physics. So if you can use it for string theory, you can just reuse all the tools you know. But also it can give you some effective models for condensed matter where you can have like effective extended objects. So it could be also interesting in more general applications. So here it's a lot of technical words. I don't want you to remember all of them. The main point is that a string amplitude, so it's like the probability for strings to interact between each other, are described by a lot of data. But the main point I want to say is that you need information about Riemann surface and their moduli space. Why a Riemann surface? So a Riemann surface is a 1D complex surface, so it's a 2D real geometry. So for example, you have the sphere or the donut. And so you can see the Riemann surface as what you get if you take many strings coming together and interacting and just cutting off the legs. So you can imagine, so here it's a sphere with like 3 holes. You can imagine that if I attach my strings there, the strings will interact in this region of space-time. In the same way, if you take this torus and you cut some holes and attach strings, it will be like strings interacting with one virtual quantum strings running along a loop. So it's why you see Riemann surface very basically. And when you have Riemann surface, you have also what we call moduli space. So it's a set of all topologically indifferent surface. So for example, in the case of the sphere, if you take this disk and you move it somewhere else, it will become another surface. So you have many surfaces like this, which cannot be related by diffeomorphism. And it causes this moduli space. So I will come later with more pictures about this concept, but it's really like the 2 keywords you need. Now the point is that Riemann surface are very hard mathematical problems in general. So many problems have been solved, but many more remain. So already here we are stuck in string field theory to rebuild the full theory because we don't understand Riemann surface well enough for this. So now here it's a list of changes for string theory. So first, as I said, you have the huge number of compactification. You have difficult math problem, which can be NP complete or NP hard, or even in some cases undecidable. The methods from algebraic topology are very cumbersome, and you rarely get closed form formulas, so it's also complicated. Here there is an interesting talk where Lucas is giving an example. So he wants to compute some dimension of a subspace, and the result is something like 5. But to get this 5, you need first to add and subtract numbers which are around 10 millions. So you have like 10 million something minus 10 million something and so on. And you add, subtract many terms, and at the end you get 5. And so, you know, like you could get that there is a simpler way to do it than just go to these very big numbers. And then, as I said, you have all this difficult problem in complex geometry, which have occupied mathematicians for the last 100 years. So what I propose in this talk is to use machine learning to solve these different problems. I mean, not solve, but already start to give indications. So the goal will be so I will have 2 goals. So first I will explain 2 different geometrical problems which we find in string theory, which we want to solve with machine learning. And then I will also briefly explain why we can use insights from QFT to improve machine learning. So we have to show that the interaction goes in both sides. It's not just physics which needs AI, but also AI can need physics. So there will be 3 topics. So first, it's odd number in CCs. Minimal area vertices in string field theory, and then this neural network quantum field theory correspondence. And I also worked a bit on machine learning for lattice simulation, but I will omit this topic today. Okay, so I will move to the machine learning for Carabio manifold. Is there any questions until now? Okay, so as I mentioned in the introduction, this complete intersection Carabio manifold are like the simplest Carabio manifold you can get. Carabio manifolds are very complicated geometry, so we don't really care about the precise definition, which is here, but it's not important. However, complete intersection is a bit simpler to grasp. So what is an intersection manifold? It's just a manifold you get by intersecting other manifolds. So one very simple case is here. If you take a three-dimensional sphere and a plane and you intersect the two, you just get a disk here. So the disk is in an intersection manifold. Now, the point that you can build a Carabio manifold in this way, instead of using like real space like this, you need to use projective space, which are the space of line in one more dimensions. So you take this big ambient space and you will start to select hypersurface. Hypersurface are just polynomial equations, like here. So like this three equation, it's polynomial. So you can describe an hypersurface in this way. So you should just, for the purpose of this talk, understand that Carabio manifold has complicated set of hypersurface equations. So without entering in the details, you can describe this set of equations by a matrix of integers. So you see here you have, so if you start with a product of zero projective space, then you get a matrix which is non-squared with two constraints. And so given this data, so which completely characterize your the topology of your hypersurface, you want to be able to extract the topological information for your surface. Okay, so here are some examples, but very briefly. So to give some idea of Carabio manifold, so sorry, it's not Carabio. So P1 is a sphere. In one dimension, you have a unique Carabio manifold, which is a torus. In two complex dimensions, you have two Carabio manifolds, so one which is called K3, and the other is two copies of the torus. And then here you have three folds. And when you see, I say like you can describe a Carabio manifold by a set of equations, it's what I mean. And here the point is that in each equation, you should have a unique power of the variable. So here you have 3x, 3y, here 1x, 1y, but you cannot have, for example, here 3x, and 2x. It's necessarily the same power, which is why at the end you can just, so in the matrix here, what you encode is the power you get in each equation. Yeah, sorry, here. So you see first equation is 3 in x, 0 in y. The other one is 0x, 3y, and here it's 1 and 1. Why do we care about topology? The first is because we don't know the metric for the Carabio manifold. So we cannot just understand the full geometry by itself. We need more. So there is also recent progress to approximate metric with neural network, but so it's not the purpose here. The purpose here is to extract this topological information, which is already good to understand the big aspect of the low energy models. So for example, if you want to know the number of fermions you have, topology is sufficient for this. If you want to know the interactions, topology is also sufficient to describe the interaction of your model. So already with this, you can have an idea if you get close to the standard model or not in terms of general properties. So you have many topological properties, and I will focus on the Hodge numbers, so which are related to the number of harmonic PQ form. So again, not important, just remember that it's some very useful number for this for the topology. So I will focus on two different data sets. So the Carabio 3-fold and 4-fold built from complete intersection. So you see that you get matrices 15 by 18 and 16 by 20. The entries of the matrices are integers, so from 0 to 5 and 0 to 6. Here are the distribution for the 3-fold. So you see here it's a nice kind of Gaussian distribution. Here it's a bit more nastier. So this problem, in fact, will be harder to solve. For the 4-fold, we get this. So again, this one is quite simple. The other are not as simple. The main difference between the two is that in the first case, we have 8,000 points. Here we have almost 1 million. So obviously, if you do machine learning, the second will work better just because you have much more examples. Okay, so the philosophy is to start with a data set and derive everything from the configuration matrix without using any insight from math. Because there were a few papers where they didn't derive everything with machine learning because they say, oh yeah, we know there is this simple relation in mathematics, but here I wanted to take this perspective. Okay, you get some geometries for which you don't know the theory and you still want to try to understand the formulas. So it's how we approach the problem. Okay, so given the time, I will be very quick. So we used an inception neural network. So the idea is that we do convolutions in parallel. So we repeat this several times, and at the end we just concatenate the results to make the prediction. With this kind of networks, it's interesting because we have much less parameters than other networks which try to solve these problems. But the second point is that here we are exploiting the structure of the equations because we know that we have a list of equations, and for each equation we have a list of manifolds. So the fact that we have parallel convolutions, in fact, is like scanning over the different manifolds and scanning over the different equations. So here are the performance. So we tried various other non-neural network algorithms. And as you see, it's very clear that already convolutional neural network works much better for the first odd number H11. And if you use the inception neural network, we get 99% accuracy if we use 80% of the data as training.
I have a question. What is your data set? If I understand, you are not able to reproduce coupling constants of fundamental forces. Yes, so what did you use, like masses of fundamental?
No, so here it's physics. So to extract this data like masses and coupling constants, you need the metric on the surface, which we don't know. Here, the odd numbers, for example, will count the number of fermions family. So it's not even the interaction. It's one step before. It's just knowing how many fermions I have. So for example, in the standard model, you have the electron, muon, and tone. So here the odd numbers will tell you how many such things you have. So you need to get 3.
So here, I remember beginning of your talk, you assume low energy.
I don't assume. So what I'm saying is that you want to go at low energy at the end, and you need to know the number of fermions family at low energy. But here now I went to the mathematical side, so I don't have any physics at this stage. So here I have the Scarabeo manifold with this configuration matrix describing the manifold, and I want to get the odd numbers. And just for this particular class of family, all the odd numbers have been computed. So here I know the results, so it's just supervised learning. And indeed, if you know the H11 and H21, you can get the number of fermions, but you don't know how they interact, like what is the interaction strength with the other field.
So it's not a problem, like for example, low energy, like QCD. QCD, you don't care if you would like to test it or not.
No, I care, but I can't yet. It's even harder. So here in string theory, we are just at the level where we just want to know if we can get 3 family of fermions. So we want to get QCD later, but it's much harder. Another question you can ask is what is the gauge group? So in QCD, it's SU3. So already here you can ask, not with odd numbers, with other topological data, do I get at least a SU3 factor in my group?
Let's assume you reverse the problem. Say, I will do it at high energy. So QCD, naively, I would say it's much easier. Like for QED or other interaction, it will be problematic. So you can do both.
So what you say high energy for QCD is still very low energy for string theory.
Okay.
Because string theory is so high that if you say okay, I just see QCD and I don't care about the other excitation of strings, you're still at low energy for strings. High energy for us, but very low. So you have very many order of magnitude between the two. And as you can see, okay, for H21, we managed to get 50% accuracy in the best case, but it's not great. And we never, I think we managed to go to 55 in some recent attempt, but H21 is still not solved. Okay, I'm skipping this. Here is just some quick explanation why these architectures work. It's what I mentioned, is that so we use convolutional layer because we need to encode the translation invariance between the different equations. We want to use weight sharing because we want to use the same operation for each of the projective space and each equation because they are all symmetric. So you can just reorder the equation and space. You should get the same thing. So it's why convolution is really the most natural layer you can use. So here I just want to show briefly the results from the return in H11. So if you do just a linear regression with 80% of the data, you get 45% accuracy. In fact, you could even reduce this, I think, to 40% and it works. SVM works good. The first paper using neural network got 37% because, it was a very simple network, so it did even worse than linear regression. And then, so they proposed better network, so to increase accuracy. And as you can see, with Inception is well above all the previous proposals. We did an aggregation study, but I will skip it for the time, just to show that everything we introduce in this architecture is really needed to get the best accuracy. If you remove one of the aspects, you just lose some accuracy. Now for the fourfolds, we used another network which is more concatenated. So again, with Inception models, but here we did some parallel processing after. In that case, we see that the accuracy is very good for 3 of the Hodge numbers, not so good for the last one, but still above 80%, so it's still decent. Okay, so to conclude, so in this paper, we did a rigorous data analysis for the thesis manifold, because one of the problems in string theory is that most people doing machine learning don't redo data analysis. They just write some bunch of neural network and see what happens. And often it's not that great. We outperformed previous paper while using less parameters. And now for the outlook, we would like to improve accuracy for those numbers we could not predict well. And we would like also to dissect the neural network data to see if we can extract analytical formula from this. Okay, before moving to the next section, is there any question?
As you said, for the data set, it's solved. And what is the idea where to apply it then? What is unsolved?
So the kind of thing here, it's in general how you compute so dimension of cohomology for a complete intersection manifold. So you have other types of intersection manifolds. Also, it's so from the point of view of math, it's only in 3 and 4 dimensions. It's not in 5 and more. So you could say, okay, if mathematician wants to address this problem in higher dimensions, they could use this networks. Also, like in general, if you want to compute line bundle cohomologies, you could try to use this kind of techniques. So you have other cases where you could do it. To be honest, I don't think it's so useful because you already have math packages to do it, and in most cases it's a bit specific. So I don't think there will be so many applications of this. The main interest from myself was to show that neural networks can handle algebraic, so data from algebraic topology, which people claimed before you can't. So it was really a proof of concept, and but I would say for string theory, I don't see many other problems where this would be useful now. Okay, so I will move to the next section on machine learning for Riemann surface and string field theory. So as I said, the Riemann surface is a 1D complex manifold, and so we call it sigma Gn. So n is a number of marked points. So for example, if you look at the sphere here, I have written many points on the sphere. So these are points which I will number, and I will track their position. Then I will have G hosts. So from the point of view of string theory, the hosts correspond to quantum groups. So it's like in particle physics where you have virtual particles. And the marked points correspond to incoming and outgoing strings. So the simplest manifold is a sphere with n points. And here I have a torus with also a few points. Now the point that, as I mentioned, you have Riemann surface, but you can deform them. So what I want to keep track, which is important for string theory, is also the inequivalent deformation of Riemann surface. So if you look at the sphere with n points, possible deformation are just moving the points around. So here I have put some arrows to just say that this point, in fact, I could put it there. It would be a different surface because the point, which has some number, is somewhere else. I can move all the other points. So here you see that if I have n points, basically my moduli space is just all the possible location for the n points. So it's like Cn. For the torus, now I can also move my points anywhere I want on the torus, but I can also deform the torus. So here I have two circles, one running here, so the small circle, and one big circle. So I can just like squeeze and move my torus. And now you can ask, what are the possible value of this tau? It's here. So let me write tau as a complete combination of tau 1 plus I tau 2. The possible value of tau are inside this band here. So I don't want to show it, but just to tell you that, okay, here is how it looks to have a moduli space. So the moduli space of this would be all the possible tau in this space, plus all the possible position for my marked points. So now in string field theory, again, I don't care too much about the beginning. I just want to tell you that there is a conformal field theory, which means that you have some scale symmetry in the problem. This CFT, you can see it as a kind of, so as a quantum mechanical system. So you have some Hilbert space, and the string field is just some very complicated states in this Hilbert space. Now when I write the action, so it will take this form. So from the action, I can extract everything I want. I can compute the path integral, scattering amplitude, equation of motion, dynamics, everything. So this action encodes all the information. It was complicated, but the main point is that here the string vertices, VGN, are something which take n copy of the field and give me a C number. So without going in the details, to build the string vertices, I need correction function in the CFT. So this I don't care in this talk. I need local coordinate on the Riemann surface, which are part of the moduli space. So you see that this VGN will be associated with Riemann surface with G holes and N points. So for each such surface, I want to have what I call local coordinate patch, and I will show a picture after. And then for each moduli space, I need to extract some subspace which I call the vertex region. Okay, so it's some data I need. I will not explain why and so on, but it's a fact. So here is some motivation for that. So first, here I have some surface with two holes and 2 points. Now on each of the points, I want to introduce some small regions. And instead of using the same coordinate as of the rest of the surface, I want to use coordinates which are just inside the disk. So my local coordinate map will be something which takes me from this region to the disk. And I will do this for each point. So it's what I need, some local coordinates. There are some constraints, but we don't care. But I need this data. Then when you have the moduli space, in fact, you can split it in 2 different regions. So you have one region which I call vertex, and the other is propagator. So what's the difference? So when I have strings coming together and interacting, they can interact in 2 ways. Either all the strings come together, interact, and that's all. So you can imagine as 2 strings coming, interacting, and then 2 strings coming out. Or you can see this as 2 strings coming in, creating the new strings, which then decay into new strings. So you have these 2 kind of processes. And it happens that the moduli space of Riemann surface can also be partitioned according to this different process. To write my action, I need to find the gray area, which corresponds just to process of this form. If you know QFT, it's because I want to write the Feynman rules and so extract the Feynman vertices. Here it's a very brief summary of this. So again, not be afraid with the technical words, but the main point is that on the left-hand side, you have geometry. So here it's just pure Riemann surface problems you could solve in math course. On the right-hand side, it's string theory. And so the CFT is giving you a map between the 2. But the main point is that already here you have many problems you need to solve. And to solve this, you don't need string theory. You just need to ask the question on the geometry. And so for the rest of this section, it's where I will focus. Okay, and I will need to hurry. So here my goal from the physics side is to construct my string field theory action using machine learning, so that I can then extract numbers and really try to make more predictions. From the math perspective, it's just to construct function and subspace of moduli space. Okay, let me move quickly. So the upshot is that there is one particular parameterization of this problem, which is called the minimal area. So in that case, I want to construct the vertex using a metric which satisfies 3 properties. So the first is that it has a minimal area on the Riemann surface, so you cannot find a metric with lower area. You also have a bound on the length of the shortest closed geodesic, so it's a systemic geometry problem. And you also have some bound on the length of internal foliation. Given all this, you can build the metric. From the metric, you can extract the local coordinates and vertex region. Now, for the case of sphere with endpoints, we can construct this metric of minimal area using what is called Strebel quadratic differential. So it's fixed up to the moduli parameters. And this is good because a metric will depend also on the point of your surface. So it's a complicated object. Here, this Strebel differential don't depend on the point on the surface. So it's kind of simplifying the problem of what I need to compute. Okay, and so for the state of the art, we have an analytic solution for n equals 3, numerical for 4 and 5 from 20 years ago. And there's also a proposition for a convex program for any G and N, but it has not been implemented. Okay, so the quadratic differential has this form, and the point is that here you just have the CI parameter which are not known, which are called accessory parameter, and you find in the UV uniformization problem. So it's what I want to find. Okay, this I will keep also. The point that finding this CI is a difficult math problem. And you can show that there is some constraint. So if you define the length in the complex plane between 2 points like this, so with the square root of this phi, you can show that a necessary and sufficient condition to have a Strebel differential is that the imaginary part of this distance between any two zeros of phi is 0. Which means that in fact this defines the real proper distance between zeros of phi. Okay. Then you can define the vertex region by the bound on the length of non-contractible curve. You can define an indicator function which tells you if you're inside or outside the vertex region. And the way I want to solve the problem is by computing the C using a complex neural network. So for my loss, I will just sum the square of all this imaginary part I wrote before. And I will minimize this with gradient descent, such that this neural network will just reproduce me the C. Here it's a very nice problem because we know that for a fixed C, there is a unique Strebel differential. So we can expect this loss to be almost convex. So it's a very nice and well-posed problem. For the training set, we just do uniform sampling in the moduli space while removing also some small disk on the marked points to just improve the convergence. So here's my training set for the first case. In our case, so we use for the neural network a fully connected layer with C-ReLU activation function. We train with 100,000 points. And for the static here, as you see, the mean loss we get is 10 to the minus 7, which is very good and efficient. The upshot is that it's not sufficient. Now we get some we will need better precision, but as you see here, we reach the limit of the float 32 precision. So we need to work with float 64. But we need even more because when you want to improve to train the neural network here, gradient descent just freeze because the number is too small. So you need even more than working with high precision. Okay, here are some curves just to show you that, okay, it converges very quickly to 10 to the minus 7. Errors are very small in general. There is few exceptions. Here we have an analytic solution, and as you can see inside the training windows, it matches the analytic solution, and it even extends a bit outside on one side. And here we can even plot the solution in the complex plane. So from this, what we want to do later is to use symbolic regression to get the analytic expression. Okay, so we'll just skip this. For the vertex region, here now it's a supervised problem because we can compute everything. It's just very expensive. So we just want to train a neural network to say if a point is inside or outside the region. You get this kind of figure, so we get almost 100% accuracy. And if you plot the probability for a point to be inside or outside, you get something which is very sharp. So for example, here it's a boundary where the probability is between 1% and 99%. So as you see, it really goes from 0 to 1 over a small space. So from here, you can also try to do symbolic regression. And in fact, my collaborators use this information to extract analytic formula of which this curve is a solution. So here it's the idea that, okay, you do numerical, but then because you have your neural network and it's a proper differential function, you can just play with your neural network to try to extract new information. You can also compute some observables. So we showed that we reproduce the observables computed previously. And so to summarize this part, so we developed machine learning technique for Riemann surface. We provided a new method to construct endpoint string vertices, and we think that our method will scale higher than the previous ones. Okay, so we need to improve precision, generalize to higher endpoint function, and also use this to compute string effective action. So given time, I will just skip most of this part. I just want to say that, okay, overall, we know that neural networks are very hard to train. So it's a black box, and it can be very expensive, like if you think in terms of GPT, where you need months of training to get something. So the idea would be to use tools from physics to try to improve the training time, in particular the hyperparameter selection. And so there is this neural network QFT correspondent, which says that if you take a statistical ensemble of neural networks, you can associate a QFT. So you can extract many information of this ensemble directly from the QFT. So you don't have to do the training or hyperparameter selection. You can do this computation on the QFT side. The main result we got is that if you vary the standard deviation of the weight distribution at the initial time, so before training, it's equivalent to a RG flow. This means that if you want to initialize your network with different standard deviation, do training and so on, you know that you can predict everything which happens if you change this parameter just using QFT. So in fact, you just need to fix the QFT parameters. You do your training with one value of the standard deviation, and then renormalization will tell you what happened for other value of this parameter. So the hope we have would be to generate this procedure for other parameters, so that you don't need to do hyperparameter tuning. You just need to train for one set of hyperparameter, and then you use flows in the space of function from physics to tell you which parameters you should select. I will just show one plot. Okay, so here it's kind of this idea that for simple tasks, it's fine to use empirical insight. I just use brute force and solve the problem without asking too much question. But for very complicated tasks, it's good if you have a more general procedure and try to understand the structure of the problem. So it's what we want to achieve here. And in terms of figure, okay, here, as you can see, so in the QFT, we need to have a quartic coupling. So it's a interaction between, like, say, 4 neural networks. And we have a prediction for this coupling is that it should solve this equation where sigma W is a standard deviation of the initial weight distribution. And so the blue curve is what we measured on the computer by setting up neural networks and measuring correlation between the outputs. And the orange line is a fit. And then we compared the fit with the theory, and as you can see, it agrees extremely well with this equation derived from renormalization theory. Okay. Now to conclude the talk, no, not this here. So also I presented a few results of machine learning for theoretical physics and math. So it will show that it's completely matter to address this kind of problems. And I did not have too much time, but I also wanted to argue that physics can provide also tools to improve machine learning and neural networks. So it will be interesting to really work more on this aspect. And also next, in terms of project, I'm working on I'm part of the BAC project, which I'm at developing benchmarks for quantum computers, in particular analog computers, the Pascal machine type. And one problem I would be interested in is to use machine learning to compute entanglement from incomplete measurements, so to characterize the state you have in the quantum computer. Thanks a lot.
Any questions for all? Yes.
As for the second model, and there seems to be some conditions to satisfy. How do you impose the machine learning model to satisfy that condition?
The Riemann surface, you mean?
second one, I don't remember exactly.
This problem you mean, or?
Yeah.
Yeah. How do I impose like this?
Yeah.
So this is what I'm using in my loss condition. So here it's my loss.
Yeah.
So I just take all possible combination of the pair of zeros. I take the square and I sum over all combinations. And so this I just minimize using standard gradient descent.
Okay, so
So it's in supervised learning in the sense that, so it's more like optimization, but instead of just solving point by point, I will solve, like, optimize the neural network.
okay,
So
so not strictly satisfied. Not strictly satisfied.
yes. I mean, it's not strictly satisfied, it gets very close, but here, as I was showing, here you see the mean value is 10 to the minus 7. So here it's the sum of all these constraints. So it means that most of the conditions are like 10 to the minus 8 something.
We consider this as more like physics info neural network or something like that, or something different.
It's a bit similar for the idea. Just, I would say my understanding is that physics informs that you will just solve the equation normally, but then you will use some additional physics constraint to kind of help converge in the good directions. Here I don't have any like L2 loss or anything. I'm just optimizing the mathematical constraint directly.
Okay.
But the idea is a bit similar. Is that physics, you know, you want to satisfy some physical equation. Here I want to satisfy some mathematical equation.
Other questions? I had one about the perspective at the end with the correspondence between QFT and neural networks. So do you expect for this correspondence to help for all types of neural networks, or more for certain types?
Yeah. So you can prove that you can associate a QFT for most of the architectures. So even transformers and all this, you can have a QFT. The main problem is how you will be able to fix the parameters of your QFT. So one way is to do it numerically. So in principle, you can at least have like numerical representation of the parameters. But yeah, you have a math theorem which tells you can write the QFT. Then in terms of usefulness, it's not so clear to me how much we can, because one drawback is that, okay, in principle, you do less hyperparameter tuning, which is interesting. On the other hand, you have to train the statistical ensemble. So you still have to train many networks. So maybe you trade the cost of hyperparameter tuning to just training many networks. I think there is one paper, in fact, using this kind of things for transformers.
Interesting. Other question? No? And we can thank Harold again.